And this is going to lay down the foundation for one more interesting algorithm, right? So how can we actually solve this question? How actually we can solve this question? Now you can see that we have to do something better than order of n log n. And if I talk about space complexity, then space complexity also we are expecting O of 1. This is the space that we are expecting. Okay. In that case, you need to do some kind of rearrangement. Okay. At last, what do you want? At last, we want the fact that there is some left part which has all the elements less than p. Then probably you'll be having a p, and then all the elements greater than p. Can I say that? This kind of a rearrangement we are looking at, right? This kind of a rearrangement we are looking at. Okay. So at last, what if somehow we have a kind of like a value I, where the ith index is going to represent where should we put p? Everything to the left of I we should put less than p, and everything to the right of I will be greater than p. If let's say something like this, if we are able to do, probably we can actually rearrange ourselves. Okay, so let's see. So we have something like 963148. Okay, this is the initial set of elements that we are having, right? Okay, so what we are going to do is let's say we'll start I from here. And we will keep one more pointer j. What is j going to do? J is going to check the current element, and I is going to maintain the partition. I maintains the partition. Okay, you'll see in a moment how. If let's say you have a value p, we will check if the element at j is this value less than p. Is this value less than p? No. We move ahead. Is the element at j less than p? No. We move ahead. Is the element less than p? Is this element less than p? Yes. So what we do is we will swap this element, that is the element at I and element at j, and we move ahead. And can I say currently everything to the left of I is less than p? Previously, when I was here, everything to the left of I was less than p because we were having no element less than p, so it was all empty. But now everything to the left of I is less than p. Okay, let's keep on moving ahead. Now, of course, 9 and 3 swap themselves. So 9 to we already compared, so we do not need to do anything for 9. We'll just move j ahead. Is 1 less than p? P was equal to 4. Is 1 less than p? Yes, it is. So again, we will swap 1 and 6 and move I ahead and move j ahead. And can you see everything to the left of I is less than p? Now, is 4 less than p? Is 4 less than p? No. But we can say that 4 is what? 4 is equal to p. So this is actually the element p that we were looking for. Can I say that? So what we will do is we will have a variable p index, and we will somehow reserve it somewhere, right? We will somehow reserve it somewhere. Okay. For example, one thing that you can easily do is the moment you realize that the current element is equal to p, you swap it with the last element so that we have the element p at the very last. Okay. So let's say we swap it with 8 and 4. Okay. Now you know that your p element, your given p element is at the last, and this is where you have j. Okay. Cool. Now, is 8 less than p? No. And then you move j ahead. Now j is at the last index. Either j will be equal to pivot or somebody else made it the pivot. So we do not need to do anything with this. And now can I say everything to the left of I is less than p? Everything from I to the right of I is greater than or equal to p. And we know where is the element p? At the last index. And where should be element p? Element p should be at the ith index. So what you will do is you will swap 4 and 9. And can you see in a single pass in O of n time complexity and O of 1 space complexity, can I say we have done the rearrangement? And this is a 2-pointer algorithm. You can say that we just use a 2-pointer algorithm. And how we got the intuition for the 2-pointer algorithm is that we were able to identify the fact that after a few iterations, few things will be less than p, few things will be greater than p, right? So if we can maintain a window, if we can maintain a bucket, that the moment we realize that an element is less than p, we put that element in this bucket and keep on increasing the size of the bucket. This gave us an intuition for 2 pointers. This algorithm is called as the partition algorithm. An interesting fact about partition algorithm is one thing. Now, do you realize that after partition algorithm, everything less than 4 is to the left of 4, everything greater than 4 is to the right of 4. Now just think about it. For a moment, forget about the right part, only take the left part. Now in the left part, let's say we again assume an element p. Let's say I assume the element p as 1. And I rearrange every element such that everything to the left of 1 is less than 1, everything to the right of 1 is greater than 1. And apply the same partition algorithm again here on the left half. Don't you think it will become 1, 3? If let's say p is equals to 1, then after the partition algorithm, this will become 1, 3. Can I say that? And let's say I do the same thing here on the right half. Let's say I pick the value p as 8. Everything to the left of p is less than 8. Everything to the right of p is greater than 8. Do you guys realize that if I apply partition on the left half and if I apply partition on the right half, then we will be able to eventually sort the array only, right? For example, let's say something like 5, 4, 3, 2, 1. Okay. Let's say we take the p element, and this element p is also called as the pivot element. This p is also called as pivot, right? Because around this element only everything is rearranged. That's the pivot. So let's say if I take the pivot element p equals to 4, everything to the left of 4 should be less than 4. So let's say we got something like 2, 3, 1, 4, 5. Okay. Can I say that? So we have rearranged, we have done the partition, everything to the left of 4 is less than 4, everything to the right of 4 is greater than 4. Can I say right half is already sorted? We have to check the left half. Now in the left half, let's say we took the pivot as 1. Everything to the left of 1 should be less than 1. So let's say I arrange it like this: 1, 3, 2, 4, 5. Can I say in this part, everything to the left of 1 is less than 1, everything to the right of 1 is greater than 1. Now, let's say I apply partition on just this part. Previously, I applied partition on this part, this part. This is now sorted, this is now sorted. If I apply partition on just 2 and 3, let's say I take the partition element as 3. So how the rearrangement should look like? Everything to the left of 3 greater than 3, everything to the right of 3, sorry, everything to the left of 3 less than 3, everything to the right of 3 greater than 3. You can see this part is also now sorted. So if you keep on applying the partition algorithm on the left half and the right half, what you will realize is that eventually, after a bunch of recursive iterations, you will be able to sort the array. So let's say if I write a function f, which takes an array, it takes a start, it takes an end. And what it does is, based on some pivot element, based on, let's say, some pivot element p, it applies partition on the array based on the value p, and returns us the index I, where p is present. Can I say what I can do is, I can recursively go from start to I minus 1 and I plus 1 to end. Can I say that? And repeat the same process, that do the partition on the left side, do the partition on the right side recursively. This methodology of sorting the array is called as quicksort. That's it. If you know the partition algorithm, you just apply the partition algorithm recursively on the left half, you just apply the partition algorithm on the right part, and eventually your array becomes sorted. How cool is that? Yes, Rupa. How many guys understand what is going on? How many guys understand what is going on? How exactly partition algorithm is working? How many guys get a hang of it? And do you guys realize that if you keep on repeating the partition algorithm on the left half and the right part, you can eventually get a sorted array? Shubham, which part were you not able to understand? Yes, Nihal. And can you guys realize this is again a divide and conquer technique, just like how we were doing it with merge sort, right? This is again a divide and conquer technique, yes or no? Yes, Manch, because if you will use sorting, like let's say you use the best sorting that you know as merge sort, then for one partition iteration, you need n log n time. Here for one partition iteration, I'm taking order of n time. Okay. Let's take one more example, guys. Let's take one more example, okay? Yes, it is called quicksort. Now, let's say we have the array like this, 9, 6, 1, 4, 8, 3. Okay. Let's say if you see one interesting thing in this quicksort algorithm, we have to decide what should be the pivot element. We need to decide what should be our pivot element, because on that pivot element only we are going to do the rearrangement. Okay. Let's say I fix the pivot element to be equal to the largest element every time. Right. So I fix the pivot element to be the largest element. So here in the first iteration, p is equals to going to be 9. If you apply partition algorithm with n iterations, you will get something like this: 6, 1, 4, 8, 3, 9. Can I say that everything to the left of 9 is less than 9, everything to the right of 9 is greater than 9? Now again I apply the pivot element. This time the pivot element becomes 8. So with n more iterations, what you will get? 6, 1, 4, 3, 8, 9. Can I say that? Can I say that? And technically with n minus 1 more iterations, because now you do not need to consider 9, right? Okay, and can you see everything to the right of 8 is greater than 8, everything to the left of 8 is less than 8. Then I again take the largest element as the pivot, as let's say 6. If you take the largest element as the pivot again, what you get? 1, 4, 3, 6 is put at the last, 8, 9. And in how many iterations? N minus 2 iterations. Can I say that? Can I say that? And so on. Can you see? For the first partition, you take n iterations. For the next partition, you take n minus 1 iterations. For the next partitions, you are taking n minus 2 iterations, then n minus 3 iterations, and so on. So what is the total number of iterations that you are doing? Can I say order of n square? Very similar to that of a bubble sort, right? So this is actually a problem with quicksort. In quicksort, if you choose the pivot element wrong, then your complexity of the algorithm can go too high, too much. N square, as bad as bubble sort. Whereas for the same input, 961,483, for the same input, if I say 961,483, if for the same input, let's say I took the pivot element as, let's say 1, 3, 4, 6, 8, 3, right? If let's say I took the pivot element as, let's say 4, then everything to the left of 4 is less than 4. Let's say 3, 1. Everything to the right of 4 is greater than 4. 9, 8, 6. So how many iterations you required? In n iterations, you are able to reach here. Can I say that? Can I say that? Okay. Now, on the left half, you apply partition algorithm again. Can I say there are approximately n by 2 elements here? Right. So in one iteration, you will get these n by 2 elements sorted. And here, if I take the pivot as 8, pivot as equals to 8, can I say in one pass, that is of n by 2 elements, in order of n by 2, in one pass, we will be able to get 6, 8, 9. Can I say that? And here we'll get 1, 3. So in n by 2 pass here and n by 2 pass here, we sorted the whole array. So technically we just took how many more iterations? N more iterations. N by 2 here, n by 2 here. Why? Because in this algorithm, we were again and again choosing the pivot element to be the middle element, the median element or the middle element, right? So it's all about what you choose as the pivot. If you choose the wrong pivot, you can be in a pretty worse situation. Like if you choose something as smallest element of the array or largest element of the array, the complexity can go as bad as order of n square. But if you choose the right pivot, let's say the middle element of the array, the complexity can go as n log n, right? Now the question can come to your head is that how to choose the pivot? Because if you choose the largest element, it is already bad. If you choose the middle element, then you have to figure out what is the median of the array, right? If you decide the fact that I will always choose the median element, then you have to find the median. Can I say that? If you have to find the median, that's an overhead. That is why there is a concept called as randomized quicksort. What is randomized quicksort? In randomized quicksort, you randomly pick a pivot. You randomly pick a pivot. Now just think about it. If let's say you have a 10 length array, what is the probability that every time when you pick a pivot, you always pick the largest element as the pivot? Like you are going to pick the pivot, let's say 7, 8 times, right? You are going to pick the pivot 7, 8 times. And let's say the array is of 100 length or 1000 length or 10 length, whatever length you have. Do you think, or I would say, do you agree that the probability of getting the largest element every time as a partition, or I would say every time as the pivot, is very less? Can I say that? Like you are randomly picking. Let's say if I give you a box of some elements, don't you think it is one of the very least probability that every time you pick the element, you are picking the largest element? Like first you picked 9, then you picked 6, you picked 8, then you picked 6, then you picked 3, then you picked 4, then 3, then 1. Don't you think the probability of this event is very less? Can I say that? What will be the probability? For example, 1, 2, 3, 4, 5, 6. There are 6 elements. What is the probability to pick 9? 1 by 6. Then after 9, what is the probability to pick 8? After 9, the probability to pick 8 is 1 by 5. Then the probability to pick 8, after 8, the probability to pick 6 is 1 by 4, and so on. Can you see this is going to eventually become a very less value? Right? This is going to eventually become a very less value. So the probability of this event that you every time pick the greatest element only is going to be very less. And you're going to somehow, on an average, pick something in between. Sometime you might pick the smallest, sometime you might pick the largest, sometime you might pick something somewhere in between. Can I say that? Can I say that? And this randomized quicksort, if you keep on picking the pivot as the random element, this gives you a average complexity of n log n, right? But worst case complexity, like you are the most unluckiest person on earth, and you got the worst case that every time your algorithm is picking the pivot, it is picking the largest or the smallest, every time the same, then the worst case still remains order of n square, right? Order of n square. So this is the problem with quicksort, that although with a very less probability, but there exists a probability that you can get order of n square. And there can be a case that you applied your quicksort algorithm once, you got order of n square complexity, you run the same algorithm again, and this time you don't go to the worst case, and you somehow lie in the average case altogether. Are you guys able to get this point? Is this point making sense, guys? Okay. So quicksort is fast. We don't deny that. But in the worst case, it can be as bad as something like insertion or bubble sort. So if you compare merge sort and quicksort is a safe bet. But merge sort has a problem. What is the space complexity of merge sort? Space complexity of merge sort is order of n. What do you think is the space complexity of quicksort? Can I say for partition algorithm we are taking O1 space? Yes or no? For partition algorithm we are taking O1 space. Now the only space that will come up will be due to the recursive calls. Can I say that? The only space that will come up will be due to the recursive calls. And just think about it. Let's say you have an n length array, right? You partitioned it. Then you made a recursive call for the left half. Let's say your pivot that you picked divided your array into equal halves. Then you will make a recursive call for the n by 2 half, right? Then on this n by 2 half, again you applied partition algorithm. You divided your array into n by 4 half. Then again you applied partition algorithm. You divided your array and so on. Can I say at last, after k divisions, size of the array will be n by 2 raised to the power k. And technically, when will you stop? When the size of the array becomes 1, because if the size of the array is 1, you do not need to do any partition. So n by 2 raised to the power k is equals to 1. Can I say k is equals to log n to the base 2? So how many recursive calls will be there? From here you make a function call, from here you make a function call, from here you make a function call. So can I say you will make k function calls? And what is the value of k? Log n. We already discussed about a similar scenario for merge sort. So can I say the space complexity in the worst case is only log n? Yes or no? Because you have log n function calls. See, this is one function call. This is one more, 2 raised to the power 1, one more function call. Then 2 raised to the power 2, second function call. Then n by 8 is 2 raised to the power 3, third function call, and so on. So there will be total k function calls. And what is the value of k? K is log n. So the space complexity of quicksort is order of log n. So if at any point of time you have a tight space constraint that you cannot spend too much on the space because of the nature of the data, quicksort becomes a better choice. Are you able to get this point?